Hello, we are doing the analysis and redesign of the smoothie maker for our DFA and DFM class. So the smoothie maker is a compact kitchen appliance, basically used to blend fruits, vegetables, and other things. Some key things about it is that there's an annual expected production value of about 15 million products. And you can see the CAD here and the exploded CAD diagram as well. People who make the smoothies are a primary consumer. These include home chefs and restaurant industry. While our secondary consumer is the caterers, a little bit more specified down. Uh, so yeah, going into our functional analysis, our fast diagram is shown here with a primary function of making smoothies, secondary functions of stirring the mixture and controlling operation, and then the other functions that help support those shown on the right. All these will appear during our report.
This is our function component mapping matrix. This shows that most parts are multifunctional, and we will use this metric as the basis for the product family design.
Here we have a quad chart where we sorted all of our parts in terms of high and low manufacturing and assembly costs, as well as high and low functional importance. Some main parts, the container, the base, the top are all high cost, high importance, and some smaller parts would be low cost and low functional importance.
So the function differentiation table basically takes the fast functions and determines whether they are the same or different for the customer groups between primary and secondary consumers.
Based on the matrix and the mapping table, these parts are all split into platform and module parts. The platform parts are used the same between both functional customer groups, and the module parts are used differently, and those are just listed on the next 3 slides with justification as to why they're there.
For the product family design, we did 3 module changes between the variants, which are the containers, the color differentiated buttons, and the main body with handles. And they share 3 common interfaces. One is between the jar mount and the drive coupling. The other is the platform mounting, and the last one is in the control buttons.
Here we see a feasible assembly sequence. This follows an inside-out model, and this was found using a fishbone diagram.
For the product family assembly diagrams, the first one shows the 3 differentiating components, the main body, container, and bottom blade. And the second shows how delay differentiation is used to be able to lower the amount of product family assembly diagrams.
These are the blades. We took these and designed them better for manual assembly. There was 2 blades with a slot in the middle, and we combined the 2 blades into one part. We changed the slot to be a square hole that we could flip it and you can put it in any direction, as well as sharpening both of the blades instead of having one dull. And that way you could also flip it top to bottom and put it in either direction. This has a high importance, and the time was changed from 7.72 seconds to 3 seconds as manual assembly time.
For our modular part, for our design for manual assembly, we took the buttons. Originally, we had 3 different buttons that were in that ovular shape, and we took that and combined it into one part, and then rounded it out so it could be flipped 180 degrees. And we also filleted the edges on both the top and the bottom so it can be flipped up and down. This shouldn't change much for the cost of manufacturing, and it shouldn't have any change on the function. It took the time from 12.9 seconds to 4 seconds. And then for our design for our automated assembly, the subassembly that we chose was the connector and the blade's base. By connecting the top connector, the cone connector, and the blade space, we were able to eliminate some of the rings that were in between there that became unnecessary, and we retapped the top hole so that it could maintain its constant function. This will likely make the manufacturing a bit more difficult and a bit more costly, but it ends up taking the cost for automated assembly from 22.5 cents per part to 8 cents per part.
Looking at the button redesign, the function component mapping matrix says that the purpose of this part is for aesthetics as well as providing power to the unit. Because of this, the critical dimensions are the length and for the appearance and the depth of the part for how far you can press the button in. The tolerance on this, as is a silicone rubber, is higher than it could be because it is flexible. So using these considerations, we are going with an injection molding process to make this part. For the blades, the critical dimension is the thickness of the part, as the blades are meant to chop ingredients and provide durability. Based off the function component matching matrix. The tolerance for this is 0.5 millimeters, and it will go through a secondary finishing process to achieve this tolerance and sharpen those blades. Because of this, we're going to use a sheet metal forming process to manufacture the part, and then, like I mentioned, it'll go through the most cost-effective finishing process.
For the core connector, we performed a DfM analysis and selected injection molding as the manufacturing process. In the initial design, the estimated cost was $2.18 per part, mainly due to the operator cost. This high cost came from the maximum wall thickness, which caused a long cooling time. We then used DfM Pro to analyze the part, and it highlighted several issues as shown on the slide. Based on these recommendations, we redesigned the part by reducing the wall thickness to 3 millimeters, keeping it uniform and adding the proper draft angle. After redesign, the cost dropped to 33 cents per part, which is a significant reduction compared to the original design.
For DfM Part 2, we performed DfM analysis on the smoothie maker's blade, selecting sheet metal working as the manufacturing process. The estimated cost is around 40 cents per part. DfM Pro recommended increasing the slot width to thickness ratio, which corresponds to design guideline number 7, avoid narrow features. Following this guideline, we increased the slot width from 3 to 4 millimeters. The cost estimation increased very little by 0.02 cents. For cost comparison, we use sheet metal working for the analytical method, while for the hub quote, we use CNC machining since sheet metal working is not available. The sheet metal analytical model predicts higher cost after redesign due to increased piercing length, while the hub's CNC machining quote is lower because a wider slot allows larger cutter.
For the product service system, we determined we would do a renting system so that users would be able to rent out smoothie makers for their events and functions. This would result in better environmental impact and enhance customer service by making less waste and a way that customers could interface with the product and the company. So the way that this would work would you would join an app, reserve it, and pick up your product, use it at your event, and then return it and pay. As an overall benefit summary and our final wrap-up, our efforts improved manufacturability and assembly by lowering part costs, as well as enhancing the user's experience with the product, resulting in a positive experience. The few design critiques we have would be modularity for parts, making it so that the user could assemble and reassemble the parts themselves, as well as easily replaceable parts that people could find online, and being able to make the product accessible for people with disabilities. Thank you for your time.